Hello, my name is Brendan Thaler. I'm in Physics 2212, Section N, and this is my observations and conclusion from Lab 1 charged tapes. Before we get into it, I just want to go over a quick overview of everything we're going to go through in this presentation. First, I just want to do an introduction describing the purpose of this model and sort of the procedure. Second, we're going to do the physical experiment, running through the calculations of everything we found with the actual tape that we were using. Second, we're going to go over a quick, small glow script model where we sort of idealized everything we used in the physical experiment into the computer world. And that way we could get more accurate measurements of everything at the cost of a lot more assumptions. And then finally, we're going to do a quick conclusion with some reflective questions. So first, the purpose of this experiment was just to calculate the amount of excess charge on a piece of clear tape using Coulomb's law and superposition. In order to do this, we need to create a charge strip of tape by quickly peeling one piece of tape off of another. This was done by having a base piece of tape and then putting another piece of tape on top of it and then peeling it off as fast as we can to make it positively charged. In order to ensure that it was positively charged, we put a plastic pen, which is known to have a slightly negative charge near it, and as it was attracted, we knew that this was a positively charged piece of tape. We did this for two pieces of tape to create likely charged pieces of tape. And then when we put one piece of tape under another, and we slowly let the top one go down until the top piece of tape was repelled by the bottom to an extent that it began to float. And then we took that separation between the two pieces of tape, and recorded that as our R vector, the distance between the two charges. The principle behind this experiment was using Coulomb's law. We want to calculate the charge of the tape by finding the distance where the electromagnetic force is equal and opposite to the force of gravity on the tape. This is found by taking a constant k, 9e to the 9, multiplied by the two charges, which in our case will be q squared because we're assuming that the two pieces of tape are likely charged, have equal charges, and then divided by the distance between the two particles, q1 and q2 squared. By finding the charge, we can approximate how many electrons were lost using the surface area of the tape and the radius of an atom. And then finally, in order to calculate the force, the charge, we need to do superposition where we take the magnitude of the two forces equal to 0. So looking at these calculations, the quick ones, we did the mass of the tape where we took an approximation of grams per meter of a tape and then the length of tape. And we took the force of gravity on the top tape, which we used the mass of the tape times the acceleration due to gravity, the surface area of the tape, which is just the length of the tape times the width of the tape, assuming it's a perfect rectangle. And then, assuming that the atoms are in perfect lattice, we calculated the number of atoms on one side of tape. So the charges on the top tape, we had it with the magnitude of the force of gravity was equal to the magnitude of the electromagnetic force because there was no change in momentum to the floating piece of tape. And so we took the force due to gravity and set it equal to Coulomb's force, the Coulomb's law. And then we divided by 9e to the 9 and multiplied by 0.011 meters squared in order to get the charge squared, took the square root to find the charge of the piece of tape. Then we can use this where we divide the charge per electron to calculate a rough estimate of the number of electrons that were actually removed from the tape. And then when we do this, we divide the number of atoms by the number of electrons we found removed. And this gave us a ratio of the number of electrons removed to the atoms on the tape. And we found that most of the atoms, by a magnitude of 7, did not lose any charge. Some quick assumptions. We assumed that both pieces of tape had equal charges, that air resistance was negligible in calculating the net force, that the atoms are structured in a perfect lattice, meaning that we can just take the surface area and the radius of an atom to calculate the number of atoms on the side of the piece of tape. We took an approximation of the mass based on the ratio of tape length to the mass of the tape, and then obviously treating the tape as a point charge in our computer model as well. So you can see in this computer model we have 2 point charges that are representing the two pieces of tape. The yellow one is the top tape and the white one is the bottom tape. And we have the three major forces at play here. The red and blue forces are the electromagnetic forces in opposite directions due to like charges. And then the yellow force is the force due to gravity on the top tape. And so we see that they're in equal magnitude. Therefore, we know that we have the correct charge on the tape. Some reflective questions. If protons were negative, electrons were positive, we would see no change in this experiment because it's not whether or not they're positive, it's their relationship with one another that decides that they're going to repel each other. And then we need to be careful with handling the tape and holding it like on the ends of the tape to make sure that we don't like neutralize the charge too much when we're taking, like from when we rip it off to when we take the distance between the two that repel. If we touched it more like in the middle or like rubbed our fingers, we could be neutralizing the charge and basically disqualifying the experiment. Thank you.